So, yesterday I wrote down the expression for the degeneracy omega, okay, or the index for a particular system in heterotic string theory. And we did this for a specific choice of charges. And several people asked me why I chose that particular charge. Okay. And the simple answer is that that particular charge, I just chose it just to give an example. Okay. The actual result is known for many charges, right, but not all charges. Okay. So, typically a finite fraction of for a finite fraction of the charges, we know the result. Right. There are expressions similar to what I wrote down. Okay. But there are also other charges for which we do not know the result. Okay. So, the idea is that we take the charges for which we do know the result, and then we will try to see if that agrees with the black hole entropy, right, and that is the general philosophy. So, this was done yesterday. So, today I am going to give a similar example for type 2 string theory. So, another example. To A or to B. On T6. Okay. So, like last time, I will specify for which charges I am going to give the result, okay, and then I will write down the result. So, you take a state that carries the following charges. Okay, again I take xm equal to xm plus 2 pi rm for m equal to 4 to 9. So, 4 to 9 directions are compact and the mu directions are non-compact. So, mu runs from 0 to 3, these are non-compact. So, the state that I am going to consider will carry, right here, 1 unit of magnetic charge of G5 mu . Sorry, this should be n units, not 1. And the goal is to calculate omega n. So, calculate Here it's a function of a single variable because there is only single charge that we are taking to be variable. Okay. And again, this is a system for which in some point in the moduli space you get a black hole. Okay. That is the reason why we want to count states of this kind. And again, here I will just write down the result without giving the derivation. Okay. So, the result is that this omega is given by minus c hat of 4n, where c hat is defined by the following expression. So, we take this function and the claim is that this has an expansion of the form sum over kl Yeah, I have just put exactly. I have put a hat just to differentiate from what I wrote yesterday. Right. Yesterday I had defined also the C4k minus L square. That those are different C's. Right, because the theory is different, the system is different. So this counting is different from that one. Right. So here I put C hat. Okay. So what is the idea? The idea is that we have this function, which is a function of two variables, P and Q. And then we carry out a series expansion in Q and P. Okay, in fact, the series expansion in K is positive. The K is always positive. P can be positive or negative. Okay, L can be positive or negative. So you make this expansion, okay, and then the coefficients can be shown to be functions of only this combination 4k minus L square, and this coefficient is what we need to find omega n. So I'll just work out one example just to see show how it works. Okay, and then you can do other examples. Okay, so example, let's calculate right, because then omega 4 will be given by minus C hat 4. Right, that's the number of bosons minus fermions for this particular charge. Okay, are there any questions on this formula? Is the meaning of this clear? Yes. I'm turning him off, right? But as I said, many of those charges are related to these by duality transformation. So you can start with this and then make a duality transformation to get Ramon charges, right? But here I've taken this system where I've turned them off. Okay, but generically the point is if you are given some arbitrary charge vector, okay, then by various duality transformations you can bring it to nice form, right? And typically one brings it to a nice form, does the counting, and then uses the fact that the same counting should work in all duality frames. They also extremal, yeah. They are also we are counting supersymmetric states, right? So all of these will be referring to as extremal black holes, extremal supersymmetric black holes. Yeah, this is torus. So on torus, there is no really no tadpole condition, right? It's automatically satisfied. There is torus, no background planes, right? So it's a simple compactification. Is the meaning of this clear? Yeah, I have not derived it, right? Even yesterday, right? Somebody asked me that how did I get that? I didn't derive it. There is a derivation which I haven't given, right? I just quoted the result. Okay, after long analysis, we count oscillators and we find this result. The same thing is true here, right? The fact that this C hat is what counts these states, I have not derived, but I have given the result. But given the result, okay, you should be clear as to what it means, right? That given the, if I tell you that this is the result, you should be able to extract all the omega n's from this. And as I said, I'll just illustrate this by calculating C hat of 4. Yes. Yeah. So Q and P are arbitrary variables, right? So this is a function of two variables, P and Q. Right? Given this function of two variables, I can do a Taylor series expansion in P and Q. That's what I have done here. Right? In fact, I have done Taylor series expansion in Q first, and then P power will be automatically fixed. Right? There will be both positive and negative powers of P that we'll see that they'll get fixed. Negative power because there's a P inverse sitting here, right? So, and then K and N are integers, over which this expansion runs. And the point is that the C hat by definition is a coefficient of this particular term in the expansion. It doesn't really matter. You can think of Q and P as complex variables because it's a forward power series expansion, right? So that can also happen for complex variables. Right? We don't need to worry about whether Q and P are real, right? As long as this expansion is convergent, we can that defines this coefficient C hat. Okay, but generically, whenever you are expanding like this, it's useful to think of the variables as complex. Okay, so any suggestion of how to calculate C hat of 4? What should we do? What is the simplest term which will tell us C hat of 4 in this? K equal to 1, L equal to 0, right? For K equal to 1, L equal to 0, you get C hat of 4. So we look for coefficients of, of Q to the 1 and P to the 0, right, which is basically Q. Okay, so you want to expand this and look for coefficients of Q. So first, let's do the expansion in Q. If you are looking for only the coefficient of Q, then in this sum, sorry, this is M. This sum is, this product is over M, right, because there is an N over here. So which term will contribute from here if you are looking for the coefficient of Q? M equal to 1, M equal to 2, or both, or neither? M equal to 1? Yeah, M equal to 1 has Q, right? That's the only term that has powers of Q, right? M equal to 2 will have Q square, Q square, Q square, right? So to do a Taylor series expansion, you will only get Q square, right? You will never get Q. So only the M equal to 1 term is going to contribute. Omega of, okay, yeah, thank you. In fact, let me just see the convention. I think, yeah, omega of N, thank you. Omega of 1. So let's pick the M equal to 1 term. Okay. So the term that you are looking for is P inverse 1 minus P square 1 minus Q P square 1 minus Q P inverse square over 1 minus Q to the power 4. Okay. And now, since you are only interested in the linear term in Q, let's expand this out into that series. So this is remember P inverse times 1 minus P square times 1 minus 2QP minus 2QP inverse plus 4Q. plus order q square, right, which you don't care. So now let's do the P expansion. Okay. So this I write as P inverse times 1 minus 2P plus P square times 1 minus, okay, let's keep it as it is. And so let's write this as P inverse minus 2 plus P. And now we are looking for the coefficient of q to the 1, p to the 0, right? So I have to look for terms in this expansion which don't carry any power of p. So which are the terms? Can you see from here? If you multiply this out, right, which of these terms will have single power of q and no power of p? We need single power of q, so you only worry about these terms, right? So start with p inverse, right? Which term does it have to multiply to give a p independent term? This term, right? Because this has a p, so we get, so you only expand minus 2q, right, from p inverse times this. Then minus 2, what about minus 2? Which term does it have to multiply? So the 4q has to multiply, this has no p, so minus 8q. And then p has to multiply which one? This one, right? P inverse, so that's minus 2q. So this is minus 12q. So omega of 1 is minus c hat of 4, so that is 12. Is clear? So this is what gives the degeneracy of the corresponding state with n equal to 1. Is this clear? So I leave it as an exercise. Okay, you can do this expansion again. If you know Mathematica, it's a straightforward exercise. You can just take this, expand to any power you like, right, and pick up the appropriate coefficients, right. So C of omega of 2, omega of 2 is 56, omega of 3 is 208, and you can calculate other omegas. Yes. Yes, Q and P are just variables, right? Some variables that you are using for defining this function, right? The arguments of this function. But Q and P really play no role, okay? Because all you are saying is that you are saying, okay, you expand this in powers of Q and P, right? And identify this particular power, and that's why it defines C hat. Right? I could have called Q and P as X and Y, right? Makes no difference. Q and P have really no relation to any physical quantity, right? At least in the way I have done it, it has no relation to any physical quantity that we are counting. Right? P and Q are just variables that are used to define this function. Is this clear? Now, for studying black holes, of course, you have to want to go to large N. So, for large N, log omega again is given by 2 pi root n minus 2 log n plus corrections that are suppressed by parts of 1 over n. Yes.
Is the comma back the smooth thread from you have to go you can go.
Yeah. So these, I mean, the way we arrived at this formula is by looking at an appropriate partition function and looking at a Fourier coefficients. Yes. Particular sign. Yes. Okay. This is, we are counting the number of bosons minus number of fermions. So a priori it doesn't have to have a particular sign. Okay. But in the black hole regime, you are right that it should have a particular sign, because in the black hole regime you have said that everything is bosonic, right? Because that's an argument from a different side, right? I have not given that argument, I'll give it later today, right? So starting from the black hole side, we know that the result should be positive because everything is bosonic. Okay? And this means that when you do the microstat counting, right, even though there is a possibility that you would have gotten negative number, right, you should get positive number. Right, even though you are counting number of bosons minus number of fermions, because you know that in the black hole regime, this does become positive. Okay? But this argument works really only for large n, right? Because only for large n that the black hole description is valid, right? So for n equal to 4, n equal to 1 or 2, right, you might have gotten negative number, right? You are not getting negative number, but for a consistency, it is certainly necessary that at least for large n, you should get positive numbers, right? And this you can check here. But for this problem, I think you get positive n for positive index for all n. Right? But a priori you could have got negative number, right? Because this, the way the expansion is written, you could have got negative or positive numbers. Okay, so this result has to be obtained by saddle point analysis of the Fourier expansion. Okay, this is what I had described last time, that general principle that we have this relation over here, right? And if we write q as e to the I pi tau 1, e to the 2 pi I tau, and c as e to the 2 pi I z, right? This is like a Fourier expansion in two variables, tau and z. So you can rewrite the expression for c hat as integrals, okay, over tau and z of this function, and then you can do a saddle point analysis to find the behavior of log omega n for large n. Okay, so that's the general principle, but that one uses here. You remember what I said last time, right? How we extracted the large n behavior, right? Because if you want to expand, say, the behavior for n equal to 1 million, right? You can do it from this formula. If you have a sufficiently powerful computer, just expand it out all the way to q to the power 1 million, right? And collect all the terms and calculate the coefficient. Okay, but that's not very efficient, right? The efficient way is to rewrite this c hat as Fourier integrals of this function, and then analyze that Fourier integral using some kind of saddle point method. Okay, steepest descent. You use a steepest descent method to evaluate this integral, and that's what leads to this formula over here. Okay. Nevertheless, it is possible to find this formula by doing numerics. Okay, so I'll leave this as an exercise. Exercise, find this formula by computing omega n numerically and say up to n equal to 20. And fitting omega n a root n plus higher order terms. Okay, in fact, this log term, for example, was discovered using numerical analysis. Okay, this one I knew because this is the vacancy knocking term, right? So this one could get either from saddle point or by numerical analysis, but the log term, okay, is not part of a vacancy knocking result. We'll discuss later how this comes about. But once you analyze this formula numerically, right, just expand this in Mathematica and pick up the coefficients, right, you start seeing that if you just try to fit with this, it doesn't quite work. Okay, but once you include the log term, then the data fits. Okay, so you can try this out. It's not a very difficult problem. The function is this defines these coefficients completely. Okay, so you can just expand in any computer code and correct coefficients and then fit with this formula over here. Okay, and this will also convince you that these saddle point methods, etc., which look formal, but they really capture how these actual coefficients go. Okay, so this is as much as I'll say about the microscopic counting. Okay. And now I'll come back to black holes again. So you recall that for the Reisner-Nordstrom solution, I wrote down the solution, but I didn't derive it. Right, so you can derive it. Right, you can put in the Einstein's equation and Maxwell's equation, and you can check that that does satisfy the Einstein's equation and Maxwell's equation. But the derivation is complicated because you have to integrate a second order differential equation, right, if you want to actually construct these functions. The fact that you have this 1 minus a over r times 1 minus b over r, right, those functions, if you want to derive it from first principle, you have to first set up a second order differential equation from Einstein's equation and then integrate. And this problem would seem that it will be much more complicated in the supergravity theories. So in theories with n greater than or equal to 2 supersymmetry, the Lagrangian is complicated. Okay, we will see an example today, but in general Lagrangian is complicated. Okay. First of all, you have not just metric and vector fields. Okay. There are several vector fields and several scalars. So the field content involves scalars which are denoted by phi alpha, okay, where alpha can run over certain values, alpha equal to 1 to say number of scalars. Then we have vectors a mu I, where I running from 1 to number of vectors, and you have of course the matrix G mu nu, and the Lagrangian will be a complicated function of the scalars, the Maxwell field strengths Fi mu nu and G mu nu. So, if you want to find black hole solutions in this theory, we have to first write down the equations of motion, right, for the scalars, vectors and the metric, right, they will be all coupled to each other, and then you have to solve it, right, which looks like a very complicated problem, right. So, the question is how we solve them and calculate the entropy, because that is what you want to compare with what you have found, for example, here, right, or some other counting that we did last time in the heterotic theory. So, how do we find black hole solutions and how do we find black hole solutions and their entropy? It turns out that for extremal black holes, and those are the kind that we are looking for now, right, because extremal, these all count extremal supersymmetric black hole microstates. So, for extremal black holes, there is a simple way to get the result, okay, and this is what I will try to describe. What
the competition to advance justice with those limitations or other competition?
Well, there will be couplings between scalars and vectors. For example, Maxwell equation, the Maxwell fields may have a term like Fi mu nu, Fj rho sigma, G mu rho, G mu sigma, and then some complicated function Fij of all the phi alphas. There we will encounter terms like this for the Maxwell tensor, right, that there will be a cross term between the term that involves the normal electromagnetic field strength, also the scalars. Right. The usual Maxwell action will correspond to setting Fij equal to delta Ij, right, because that is what is the standard Maxwell action, but this is a kind of action that you have to encounter. So, this means that the scalar field equations will depend on the vector fields, the vector field equation will depend on the scalar fields, and the metric equation will have simultaneous dependence on the vectors and the scalars, right. And then of course, there are separate scalar kinetic terms which also will contribute to the metric equation. So, that is the complication, right, that so you have a differential equation in many variables, right, and the question is how do you efficiently solve them and extract the black hole entropy. Is this clear? Okay. And the other complication is that eventually we like to do calculate this in the we want to say calculate the stringy corrections to the entropy, and in string theory this is only of course the first term in the expansion of the Lagrangian. Terms like this, there are also terms which involve high number of derivatives, right, like for example the Riemann to the fourth term, right, which is general coordinate invariant, so we can add it to the action. Normally you do not have such terms in the Einstein theory, right, but in string theory you do have such terms. So, you want to add those terms and we also see what their effect is on the entropy. Are there questions? Is this issue clear? Yeah, that you have a complicated Lagrangian, and hence the question is how do you go about solving it. Okay. So, to see this you have to go back to Rice and Nordstrom and study some properties in the extremal limit, okay, that simplifies the analysis. So, go back to the Rice and Nordstrom solution to where the metric is given by ds square minus 1 minus and the extremal limit B goes to A. If you remember, in the extremal limit, the two horizons become the same because B and A differ from this plus minus sign in the expression for A and B, right? And the term is inside the square root vanished, right? So the two horizons become the same. So B goes to A is the extremal limit. So we will now take this limit in a certain way, okay? And the way we will take it is that as A and B go close to each other, we choose our coordinate system so that we get closer and closer to the horizon, right? And we will see what what I mean by this. So we define lambda as B minus A by 2. Okay, so lambda is what you want to take to 0. But instead of just setting B equal to A here, we first rescale our coordinates. We define the rescale tau time tau, which is lambda T over A square. And we also define a new radial coordinate rho, which is 2r minus A minus B or 2 lambda. Okay. So at this point, all I have done is that I have defined a new parameter lambda, and I have just used new coordinates, new time coordinate tau, and new radial coordinate rho. Right? Nothing has changed. I can just rewrite the original Lagrangian in this coordinate system. Okay, so rewrite, not the original Lagrangian, rewrite the matrix in rho tau coordinates with B replaced by A plus 2 lambda. It's not, does not rho diverge. We'll see it. Rho, so rho diverges if you keep R fixed, right? But what I am going to do is that we will keep rho fixed and take lambda to 0, right? Which basically means you are taking R to be close to A, right? That's the point I want to say, that we'll keep R rho fixed as we take the limit, right? So that we are closing in on the horizon, right? You want to see the kind of geometry that the horizon has, and you don't care about what happened far away. Right? But you are indeed right that if we try to take lambda goes to 0 keeping R fixed, then of course rho will diverge. Right? That means that in this coordinate system, the region of finite R is far away, looks far away in the rho coordinate system. Okay. So rewrite the metric in this coordinate system and take lambda to 0 limit at fixed rho, tau and A. So, okay, we'll keep A fixed, rho and tau fixed. We can always decide that we'll work in the region of space. We want to look at the metric in the region of space when rho and tau are fixed and finite. But otherwise, it's just a rewriting of the original matrix. Right? I have not changed anything. So it will it's guaranteed to be a solution to the equation of motion, where Einstein's equation is a general coordinate invariant. Right? So if we make a change of coordinates, the new metric will continue to satisfy the equations that the old metric satisfies. Is the meaning of this clear? Right? Just change coordinates and then take the limit in the way I have suggested. So, exercise show that in this limit divided first. So, what has happened here is that the horizon, the two horizons are at rho equal to plus minus 1. In this rho variable, the horizons are at rho equal to plus minus 1. You can also verify it from here. Right? The first outer horizon is at r equal to a, right? Remember the outer horizon here was at r equal to a. Right? So, at r equal to a, what happens to rho? Rho becomes a minus b over 2 lambda. 2 lambda is a minus b. Sorry, this is not b minus a. I am sorry, this is a minus b, right? Because a is the outer horizon. So, please correct this. Right? Lambda is positive. So, this is a minus b by 2. We have taken a to be larger than b. So, the horizon at r equal to a becomes at rho equal to 1, and the horizon at r equal to b becomes at rho equal to minus 1, right? That just follows from these two equations. And that is what we are saying here. The fact that the d tau squared coefficient vanishes at rho equal to plus minus 1 is a signal that the horizons have moved to rho equal to plus minus 1. So, this is a straightforward exercise, but I will urge you to do this. Right? The here, for example, as you take this limit, as you take the lambda goes to 0 limit, keeping rho fixed, r basically becomes equal to a. Okay, and that is why this has become a squared times d theta square by sin square theta d phi square. Are there questions?
I have a question from the plan. What is the difference between the air?
So, A is the event horizon because I have taken A to be larger than B, right. So, A is the outer horizon. So, you call A the outer horizon and B the inner horizon, right. So, from outsider's viewpoint, A is the horizon, R equal to A is the horizon. So, well, something special happens at the B horizon, but that is only for observer who jumps in, right. That person will feel some instability near the B horizon, but from outside we are not going to see the B horizon. Okay, so, as far as the entropy etc. are concerned, the A horizon is the important one, right, because that is what interacts with the outside observer. Yes.
So the air horizon given to the tau and the rho coordinates. Does it have a maximal?
Yeah, I'm going to just describe that. Yeah, it does have a maximal isometry. So, I'll try to rewrite this in a more suggestive way. So, you make another change of coordinates. Rho equal to cos hyperbolic eta, and then this ds square becomes Okay, this is again straightforward. If rho is cos hyperbolic theta, then this is sin hyperbolic theta square, right? That's what I have written. And here d rho will be sin hyperbolic square theta d theta square. That cancels with the sin hyperbolic square theta that comes from the denominator. So that is d theta square. And now we can see some similarity between these two factors, right? Here it was d theta square, d theta square, right? So theta is like playing the role of theta. Okay. Here it was sin square theta d phi square. Here it's minus sin hyperbolic square d tau square. Okay. So it's as if tau is playing the role of phi, okay, except that there is a minus sign, and instead of sin square theta, there is sin hyperbolic square theta. Okay. And we will see that this similarity is not a surprise, because this can be viewed very similarly as to a sphere. So rho equal to 1 is the outer one, because rho is radial coordinate, right? So 1 is greater than minus 1. So 1 is the outer horizon, because the asymptotic observer is at rho equal to infinity, right? So the looking from at infinity, you'll see the 1 at 1 first, right? Then the 1 at minus 1 will be hidden behind the horizon at rho equal to 1. So rho equal to 1 is outer horizon in this picture. Okay, so sphere, okay, sphere of this kind, we can think of this. So this is a sphere, and this has a name. Let me write it. Okay, this is called ADS2, two-dimensional anti-de Sitter space. Two-dimensional anti-de Sitter space. Anti-de Sitter. Okay, why is it called ADS2? We'll see soon. Right? This is, as I said, this is similar to sphere. So a sphere metric of that kind that we have can be thought of as a surface x square plus y square plus z square equal to a square embedded in Euclidean 3D space. Okay, so Euclidean 3D space has ds square as dx square plus dy square plus dz square. This is familiar to everybody? Right? The sphere of radius A can be thought of as an equation like this, embedded in 3-dimensional Euclidean space. Right? If you want to see it explicitly, you just have to change coordinates, right? Z equal to a cos theta, y equal to a cos theta, a sin theta sin phi, x equal to a sin theta cos phi. Okay, so this obviously satisfies x square plus y square plus z square equal to a square. Right? And then when you substitute in this metric over here, right, this a of course is a constant, you will find that the metric is given by this a square times d theta square plus sin square theta d phi square. The claim, which I'll leave to you to verify, is that the ADS2 metric is given by the surface. Let me get the signs right. By taking x square minus y square minus z square equal to a square in the 3D space, 3D space, with metric. Okay. So this looks like a space time with two time directions, right? Y and Z have negative signs, so it looks like you have two times. But once you impose this condition, right, you find that you don't have two time, you have only one time, because you can see that here there is only one negative side. Okay. And we can also write down the change of coordinates, which does that. Okay. So, well, I could have maybe sorry, I made a mistake there. There's a minus sign here. Okay. And the change of variable is Z equal to A cos hyperbolic theta, sorry, cos hyperbolic eta, Y equal to A Does this work? Let's see. So y square, sorry, is x. So y square minus x square is a square sine hyperbolic square eta, and then sine hyperbolic square tau minus cos hyperbolic square tau, that's minus 1. So that is minus a square sine hyperbolic square eta. Okay. So here you have x square minus y square, right? So that gives you a square sine hyperbolic square eta minus z square is a square cos hyperbolic square eta, and that is minus a square. Okay, so if you take these parameterizations, so this is like the analog of this. So what we have here for the sphere is what we have here. So this change of variable, okay, automatically satisfies this equation, and then I'll leave as an exercise to check that when you look at the metric, this metric, and evaluate it for this choice, keeping a fixed, you get back exactly the radius metric that I have written here. To exercise, check that this gives radius to metric. Okay. So what we learned from here is that the near horizon geometry of the Eisner-Nordstrom black hole, extremal Eisner-Nordstrom black hole, has an ADS2 times S2 factor, right? There is an S2 and there is an ADS2. And these two spaces don't talk to each other because they have different coordinates. Now the result is that all spherically symmetric extremal black holes have ADS2 times S2 near horizon geometry. Okay, spherical symmetry, as I said, supersymmetry imposes it. I have not discussed it so far, but you will eventually hope to do it, right? Maybe if not this lecture, next lecture. Okay, but if we have spherical symmetric black hole, like the Rice and Nordstrom was, and if you have near horizon, and if you take the extremal limit, you get ADS2 times S2 factor. If you don't have spherical symmetry, but you take the extremal limit, you still have the ADS2 factor, but not the S2 factor, right? The S2 gets squashed. Okay, because if you don't have spherical symmetry, there is no reason to have a sphere. Is this statement clear? Now, why is it useful? Okay, so let's try to understand that why having this near horizon ADS2 times S2 is useful. And for that, you have to mention another property of ADS2. So, first of all, the sphere. Let's look at the sphere. Sphere has a symmetry group. You know what the symmetry group of sphere is? It's SO3, rotation in 3 dimensions, right? You rotate it anyway and you get a sphere. So, a sphere, so 2D sphere has SO3 symmetry.
What master should be have?
So, that is the point. SO2 is rotation in 2 dimension plane, right? 2 dimensional sphere has SO3 symmetry, right? 2 dimensional sphere is this one. This I am calling 2 dimensional sphere because it's a its surface is 2 dimensional, right? So, it's a sphere embedded in 3 dimensions, right? That is why the SO3 is inherited, but the sphere intrinsically is a 2 dimensional sphere, right? It has 2 dimensional surface. So, in the same line, ADS2 has SO1, 2 symmetry. You can see that from the structure, right? If you make a Lorentz transformation in the XYZ space, right, with 1 space and 2 time direction, right, which is the same as 1 time and 2 space, right, because that changes the overall sign. Just if you make a Lorentz transformation on this, then the surface remains unchanged, the metric remains unchanged, because it is also a symmetry of ADS2. So, it has an SO1, 2 symmetry. Now, the SO3 symmetry on the sphere has a consequence, and the consequence is that the sphere is homogeneous. What do you mean by homogeneous? That any point on the sphere can be reached from any other point by a symmetry transformation. You can probably visualize it, right? If you just had SO2 rotation, right, rotation along in just the single axis, then you cannot connect all the points of the sphere by symmetry, right? You only connect points that are on the same small circle, right? Take the Z axis and just rotate, right? You go only along the you can go connect the points on the same small circle, but not on a small circle and a great circle, for example, right? Equator will be different from it. But because of the full SO3 rotation, you can rotate on any axis. Any point on the sphere can be taken to any other point, right? So, this is what we call that it has an SO3 symmetry. So, same property is true for ADS2. Because of this SO1, 2 symmetry, one can show that any point on ADS2 can be taken to any other point by asymmetric transformation, by one of the SO1, 2 symmetric transformation. Because all points in some sense are equivalent, right? Just like the sphere looks the same from any point, the ADS2 also looks the same from any point. Is this clear? So, you are now going to make use of this symmetry to write down the near horizon geometry. Near horizon geometry, of course, is radius 2 times S2, that I have already said from here. But we can also write down the near horizon form of all the other fields, right? The scalar fields, the vector fields, and so on. Yes.
You know, we marked up the rho and power coordinate and the theta and power coordinates because they are different coordinates.
Yes. That what I mean by that, that normally if you look at this Reisner Nordstrom, right? Theta and phi talk to R because R multiplies the d theta square by d phi sine square theta d phi square, right? So the metric in the theta phi space is still R dependent, right? The space is not a product. Okay. Here you see that the metric in the tau eta space is independent of theta phi, and the metric in the theta phi space is independent of tau eta. So you call this a product space, right? There is no dependence on tau and theta for the metric on the theta phi space and vice versa. No, it's a product, right? So it's like a plane, for example, can be thought of as a product of two lines, right? The x coordinate and y coordinate, right? So it's like you still have 4-dimensional space, right? It's not a 2-dimensional space. You have a 4-dimensional space time, but it just becomes a product, just like a plane as a 2-dimensional space is a product of two lines, right? X and y axis, and you can independently specify x and y coordinates. Is this clear? So now suppose containing you can have a scalar, so called phi alpha, then vectors, and metric. Okay, there are also formulaic fields typically, but those are not particularly relevant for the black hole side of the analysis, entropy analysis. So what we'll do is we'll identify the most general configuration of these fields near the horizon of an extremal black hole. Okay, and we'll use the fact that near the horizon of an extremal black hole, we have these symmetries. Okay, you have the SO3 symmetry and SO and 1,2 symmetry. So the scalar field phi alpha is a function of theta, phi, rho, and tau. Okay, in general. But on the horizon, on the extremal horizon, what will be the form of phi alpha? If you want that it should be invariant under the symmetries, right? What form can phi alpha take? Let's first look at the sphere, dependence on theta and phi, right? Suppose we demand that phi is invariant under the SO3 symmetry. Can you say anything about what kind of dependence phi can have on theta and phi? So remember that on the sphere, any point can be related to any other point by a symmetry transformation, right? So if you want the field configuration to be invariant under that symmetry transformation, so it cannot depend on the angular coordinates, right? So phi alpha has to be independent of theta and phi, right? Because suppose it depended on theta and phi, right? Then at two different points, it will have different values. But we know that those 2 points can be related by symmetry transformation, right? And phi being a scalar doesn't transform under rotation. Right? So, phi cannot depend on theta and phi. In the same spirit, phi cannot depend on rho and tau, because ADS2 also has the same isometry, right? Can phase factors. No, even if we are not demanding only that the mod phi is invariant, the whole of scalar fields, phi can be a real scalar, right? So, then there is a phase, right? So, the all components of phi should be invariant under theta and phi, that should be independent of theta and phi. So, on the extremal horizon, then phi alpha will be just constants, independent of rho tau theta phi. Metric similarly, okay, its structure will be fixed. It has to have maintain the isometries of ADS2 times S2, so it has to have this form, except that we can allow a slightly more general form. Okay, so I'll write this as here we call this V2. Okay, where V1 and V2 are constants. Okay, I can also rewrite in the rho tau coordinates. Okay, sometimes it's useful. D rho squared Okay, so the point is that the fact that for Reisner-Nordstrom black hole, these two are equal was not dictated by any symmetry. Right? You are not saying that there is a symmetry that exchanges ADS2 and S2. Right? In fact, there is also a symmetry. So, if we just demand symmetry, then these could be different. Right? And for a general black hole that we are considering, there is no reason why they have to be equal. Right? So, allow for V1 and V2. Is this okay? For gauge fields, it's a little more complicated, right? Because the gauge fields are tensors, right? Not invariants. Okay, nevertheless, it's because it's a it's a simple enough system, we can actually write down the form of gauge fields. So, we will write down the expression for the field strengths directly. So, first point is that all mixed components will be identically 0. Okay. So, Fi has a mu component, right? Mu can run from rho tau theta phi and mu can run from rho tau theta phi. Okay. So, if one of them is in ADS2, the other one is in S2, then it must vanish, that component must vanish. Because imagine that F has one component in S2 and other component in ADS2. Okay. Then from the point of view of S2, right, what kind of a field is it? What index does it have of S2? It has one component in S2, one component in ADS2, right? It's like a vector field, right? Because one component is either theta or phi, right? That's vector from the point of view of the S2. But the other component is rho and tau, right? That's a scalar from the point of view of S2. So, it's a vector from the point of view of S2 and also a vector from the point of view of ADS2. But neither S2 nor ADS2 has any vector field, does not admit invariant vector fields, right? This is a general result that on a sphere, you cannot have a vector, invariant vector. Right? If you rotate it, it will change. So mixed components are 0. So Fi has no mixed component. Fi theta phi can be shown to be proportional to sine theta. So let me write this as pi sine theta, where pi is constant. And similarly, Fi eta phi is pi sine hyperbolic theta, which you can also write as this also implies that Fi, sorry, theta not phi. Let me write it as rho eta. Sorry, eta tau. So Ei is constant. So Fi theta phi being pi sine theta, right? This is basically, if you are familiar with the notion of forms, right? Fi is antisymmetric in theta and phi, right? It's Fi mu is antisymmetric. Okay. So the one way to construct the invariant form, and that's the only one, is that Fi theta phi d theta d phi. Okay, if you are not familiar with this language, just take this, accept this as the result. Okay, that you get from symmetry analysis. But if you are familiar with this language, okay, that if you think of this as a two form, then the idea that this should be equal to the area form, right? And the area form in this case is square root of minus determinant g is sine theta, right? So this should be equal to, this should be proportional to sine theta d phi. And that's what leads to this form, that Fi theta phi is proportional to sine theta, and similarly proportional to sine hyperbolic theta. Okay. Here you can get it either by making a coordinate transformation from here eta to rho, okay, or directly in the rho tau space, right? You can see the area form in the rho tau space. Here, area form in the rho tau space. Here the determinant is 1. Right? So area form is just d rho h d tau. Right? That's why you don't have any other function. But the net upshot of this analysis is that once you impose these isometries in the near horizon geometry, in the near horizon region, we only need to determine a set of constants. Whereas the full black hole solution requires specify a set of functions, right? What is the R dependence of the metric? Right? That's what you are trying to look for for a general black hole solution, right? That 1 minus A over R, 1 minus B over R, you got by solving the Einstein's equation. Right? So that we don't have to do in this case, right? In fact, once you have scalars, the problem is much more complicated because you have to not only solve Einstein's equation, but the scalar field equations also will give some equation that you have to solve, right? And the scalars may have a different radial dependence than the metric. So we don't need any of those, right? Because we are now looking for some constants, not functions. Is this clear? Right? So I'll now describe what you have to solve to get this. So the action A is given by integral d4x square root of pi the determinant g times the Lagrangian density, right? This is the Lagrangian density. And the field equations of motion are delta action, delta A, delta fields equal to 0. But this one we can now write d rho d tau d theta d phi square root of minus determinant g. I'm sorry, I erased the metric. Okay, but if you recall the metric, it will be V1 V2 V1 V2 sin theta times L. Okay, because the V1 came from the ADS2 part, the V2 came from the the S2 part, this square root of minus determinant g, and the sin theta came because the sphere metric has a d theta square plus sin square theta d phi square, right. In the rho tau space, the ADS2 metric had a 1 over rho square minus 1 from d rho square and rho square minus 1 from d tau square, so they just cancel. So this is the form of the Lagrangian, and the Lagrangian density, this is a scalar. Okay. So this is independent of any of the coordinates, right? The same argument that we gave earlier, right? So when you evaluate the Lagrangian density for the background for the fields that you have chosen, this is independent of r theta, sorry, not r, theta phi and rho tau. I can use rho or eta, okay, it doesn't really matter. If I am using eta, then I have to put a sine hyperbolic theta here. So this is only a function, this will be only a function of the u alphas, ei's, pi's, v1 and v2. So let's, and then the theta, phi theta integral can be done, right? So phi theta integral gives you 4 pi. So 4 pi integral d rho d tau times v1 v2 L as a function of u alpha, ei, u1 and v2. Let's call this some function f. So then the equations, scalar equations, which are delta A delta phi alpha equal to 0, this reduces to just an ordinary equation del f del u alpha equal to 0. Okay, because there is no dependence on any space or time coordinates. F is just some function that we have here. Okay, and let's take a derivative with respect to u alpha, set it equal to 0. That's what is supposed to determine u alpha in the linear horizon geometry. Similarly, the metric equation will be del f del v1 equal to 0 and del f del v2 equal to 0. Because v1 and v2 are the two degrees of freedom of the metric, right? Let me remind you what the metric was. So ds square we are taken to be v1 times d rho square over rho square minus 1 minus rho square minus 1 d tau square. electromagnetic field equations. There are two sets of equations that you have to solve. One is a Bianchi identity. The other one you get from varying the action. So, delta A, delta F I mu nu equal to 0, right? This basically tells us, sorry, delta A I mu. This gives you okay, this is electromagnetic field equation, okay, for a general Lagrangian. This is automatically satisfied. Okay, for the field configuration that you have taken, we don't have to check anything here. Can you guess why? Why is this automatically satisfied? See, this has to be invariant under the isometries of ADS2 times S2, right? Because you have taken the field configuration to be invariant under the symmetries of ADS2 times S2. Now, what kind of a tensor is this combination? What kind of a tensor is this? So, the whole thing, let's count the index, free index. Yeah, how many free index does it have? One free index, right? Because the new index is already contracted. Right? So, one free index. So, it's a vector equation, right? And that's not surprising because you have gotten it by varying with respect to mu, right? So, it's a vector equation, and you have just said that neither S2 nor ADS2 has a vector that is invariant under the symmetries. Okay? So, if there is no vector invariant under symmetries, and if the field configurations you have chosen are invariant under symmetries, then the vector is automatically 0. Okay? You don't have to do anything to check it. You can check it, of course, but it's 0 simply by the fact that there is no invariant vector on ADS2 or S2. Okay, so due to absence of invariant vector. Okay. And same is true for here. It's true also automatic. Sorry, this is actually antisymmetric, right? So let me write this as epsilon mu rho sigma. Okay, if I write it this way, then this is also a vector. Right? The Bianchi identity is a vector. Again, by the same argument, it vanishes automatically. You don't have to check the Bianchi identity; it will be automatically true. Okay, so you only have to solve these equations. Okay, these two for the metric and these for the scalar. Okay? And these, as I said, these are algebraic equations. Okay, you don't have to solve any differential equation for this. Now, we have to still say what these parameters EI and PI are doing. Okay, so let me just say this. So, PI is the magnetic charge. Okay, that's perhaps not surprising, right? Phi theta phi is a magnetic flux that you are familiar with, Fi theta phi. B is what? B is card of A, right? So you have to take an epsilon tensor and combine it derivative, right? So F theta phi, if you multiply epsilon tensor, it gives a radial component, that's B. Because of Pi, you can identify maximum magnetic charge. Now, EI is the electric field. So there is a tendency, maybe you may have a tendency to say that EI is the electric charge. But it turns out that EI is not the electric charge. What is electric charge? QI. QI is del EI of F. Okay, and that basically is a consequence of this conservation law. Right? This basically is telling us that this combination, okay, is what is independent of the radial coordinate. Right? This is the equation of motion. So this combination is independent of the radial coordinate. So this combination calculated at infinity is the same as calculated on the horizon. So if you are trying to guess what the electric charge is by doing the horizon calculation, see normally electric charge is defined at infinity, right? Not at the horizon. So if you are trying to determine what the electric charge is just from the horizon dynamics, horizon configuration, then this is the formula that you have to use. Okay, F again is beyond V2L. And finally, I will state a result which maybe I will try to derive in the next class, and that is what is the most important result, that the entropy S is given by 8 pi square okay, with F being given by this. Okay. So basically this is saying that by just solving a set of algebraic equations, and we will apply it to Reisen-Nordstrom and see how it works. Okay. But what it is saying is that just by solving a set of algebraic equations, you can get the entropy. You do not have to solve any differential equation, right? And this is true for Reisen-Nordstrom, but also true for general theory. Okay. But this is that if you are interested in calculating the entropy of extremal black holes. Yeah, it is like Legendre transforms, exactly, right? Because we also see that it's a Legendre transform because Q and E has this relation, right? So this is like the Legendre transform of F. If you express as a function of E and P, because other than your horizon fields, but to get to the entropy, you have to do a Legendre transform. So Q is the conjugate variable to E. Qi is, sorry, EI, exactly. So E is the electric field, right? So E and Q are conjugate variable, right? You see from this relation over here. Okay. So this statement I have not proven. We will see in the next lecture. If we get time, we will try to prove this. Okay, so this is not proven yet, right? For the next lecture. But an important point is that you see that all the equations can be obtained by simply extremizing S, right? Why? Because extremizing F with respect to the U's and the V1, V2 is extremizing S, right? Because these are independent variables. Extremizing S with respect to EI is this equation, right? Because you will get Qi equal to del F del EI. So all the equations that you have to solve are obtained by extremizing S. So you have a function S whose value at its extremum is the entropy, right? That is the lesson from this. Okay, maybe I will stop and then we will continue.